Сегодня у нас в гостях доктор Милош Железны, Западно-Чешский университет. Он там наш хороший друг, товарищ, так сказать. Мы с ним участвовали в этих разных многих конференциях. Вот он приехал с нами поделиться своим докладом про мультимодальное человеко-машинное взаимодействие. Вот. Ну, в общем-то, я предоставляю слово Милошу. Милош сегодня будет говорить на английском, чтобы у нас как бы молодежь в основном, в том числе, училась не только хорошо всякие математические модели, методы делать, но и слушать, и писать, и читать на английском. Поэтому доклад Милоша будет на английском. Милош, кстати, хорошо говорит по-русски. Если что-то будут какие-то вопросы, можно задавать будет по-русски. Спасибо, Милош.
Let me continue and introduce a little bit myself. My name is Miloš Железny. I come from University of West Bohemia in Czech Republic, in Plzeň, which is the city that is 80 or 90 kilometers from Prague, and towards west, so it's Western Bohemia. University of West Bohemia has 9 faculties. One of them is Faculty of Applied Sciences, and we have both technical, natural sciences and also humanity faculties. Faculty of Applied Sciences was established 12 years ago in 1990, joining 5 departments from Faculty of Electrical Engineering and Mechanical Engineering. So we have departments of physics, mechanics, mathematics, computer science, cybernetics, which is my department, and now new department of geomatics. We established a new European Center of Excellence, which was a project donated by European Commission under some projects for development of universities. So we have for 2.5 years we have a brand new building, and we have a lot of equipment there. So this is, if you can see, this is the image of our new building. Somewhere here is my office. So, about myself, my profile started in speech processing back in 90s, and my PhD and master thesis was in speech processing, but I was interested quite a lot in image processing, so I moved to a domain processing of combined audio-visual information. So we, as speech processing professionals, joined the computer vision domain and started with projects from the domain of audiovisual speech processing. So we started these projects in 2001 or around 2000, and I will present in this presentation results and research topics in this domain that I call multimodal human-computer interaction. From the point of view of multimodality, I will speak especially about I will talk especially about the visual modality, so image processing. I will present two quite big topics: audiovisual speech synthesis and synthesis and recognition of sign language. So computer processing of these languages, especially on the visual means, or by the visual means. And at the last part, I will present the equipment that we have for solving these tasks. So I will always make some motivation to solution of the problem, then present some methods, and then present some results. So maybe I have also some demonstrations. So if you have time, we can show some demonstration. So to start with the audiovisual speech topic, I would like to present a very old scientific results or findings that we all in audiovisual speech build on. All the research is based on these old findings, or we have now new findings, but they all contribute or provide results that confirms that these original ideas were true. So even already in 1954, Samby and Polak presented a publication called Visual Contributions to Speech Intelligibility in Noise, where they provided information that the visual component contributes to intelligibility of the speech if the acoustic channel is modified by noise, for example, or by some hearing problems of person. Then I would say most cited publication in audiovisual speech at all. If you see a paper on audiovisual speech processing, it probably cites this publication from '76, McGurk and McDonald, Hearing Lips and Seeing Voices. They presented so-called McGurk effect or Bagada effect, where users or listeners were provided by intentionally mixed audiovisual stimuli, where acoustic ba was put together with visual ga. So even if you are not specialist in speech processing, you can imagine that ba uses closing of the lips, while ga does not close the lips. So if you see the visual perception that does not close the lips, you do not perceive ba, because you miss this important cue, and also you do not listen ga because the acoustic part is ba. So the combined perception of most people is that they perceive this syllable as da. So this is very interesting effect that provides evidence that the combined audiovisual perception works, and it is so robust that even if you know about this effect, you will perceive this again. So motivation can continue by explaining where we can use it. So as I told already, in noisy environment and in case of hearing impairment, we can use audiovisual component, or we can add visual component to audiovisual or to acoustic speech as a means of communication between human and machine. There is a lot of studies that provide evidences that this audiovisual perception works, that visual perception is important for humans as well in human-human communication, etc. So there, you know that there is more modalities besides acoustic speech. There is visual channel, there is eye contact, there is some gestures, and etc. If we speak about hearing impairments, we can get up to such level of impairment that means totally deaf persons, and in this case the communication already does not use audio-visual speech only, because the visual channel itself is not so informative, and these people communicate in sign language. So sign language is a main communication means of deaf people, and it is based on manual gestures provided by articulation and facial expressions. Manual component consists of 4 main properties of both hands. It means hand shape, hand position, orientation, and hand movement. Then relation of both hands. Then we have non-manual component, which is lip articulation, so shape of the lips, and the expression of face, because face expression is integral part of the sign, and sometimes the same manual gesture combined with positive expression has different meaning than combined with negative expression. So it's the case of deaf people. We can distinguish also people that are deaf from birth and people that are deaf that lose the hearing abilities during their lives. So according to age, it has different properties, and of course, if someone learns to read, someone learns to speak, and then loses hearing abilities, it is different than people that are deaf from birth. Sign languages, sometimes it is supposed that all people that are deaf that communicate in the one universal sign language, so we must say that there is a lot of differences, that there are national sign languages. Every country in Europe, almost every country in the world has its own sign language, and they even differ within one country. For example, the correspondence of vocabulary of St. Petersburg and Moscow variants of Russian Sign Language are about 70% in basic terms, and when we include also the abstract terms, it's only 30 to 40%. So it seems that we have to work with a lot of variabilities, and we cannot rely on that there is like one universal language. So when we design such system for communication of human to machine, we must take into account two requests, like for the task. And first one is intelligibility, so that the system is intelligible, we can understand, users can understand, and can communicate. And that the next level is that the system is natural, so that it is pleasant for the user to use the system. So it means, for example, in case of speech communication, that we do not use robotic voice, that speech recognition is smooth and intelligible, etc. One important and also very cited research was that one of, I think, Masahiro Mori, some Japanese researcher, who presented uncanny valley, which is a curve that shows acceptance of these technologies by people. So on the horizontal scale, we have human likeness, how the system of communication is similar to a human, to real human. And on the vertical axis, we have a familiarity, how familiar users are with such systems. And he shows that when the human likeness increases from industrial robots, from very industrial synthesis, for example, to more humanoid robots, more human-like systems, the acceptance is also higher. But then, at certain point, when it is almost like a person, then people expect it will work much better, and then every small mistake, every small unlikeness of the system makes that the systems are not so acceptable, and they look like zombie, for example. And then we expect that on the other side of the valley there is a other shore or other bank where we have a healthy person, and we want our artificial systems to get over the valley to the other side, so that they are absolutely accepted. And I think it is the task for next years of research in this domain to get here, because very good animated movies are almost here, because the movies use techniques when we record movements of real actors, for example. So you can imagine that in a movie there's a lot of actors, but one person is animated. I mean, for example, Lord of the Rings. Do you know? I think Lord of the Rings is a well-known movie, and there is one person which is completely animated, but its movements are very natural because they are recorded by real human, by real actors. So I would say sort of dynamics, sort of energy, if we can call it, are contained in this movement, and then these movements are accepted. And the idea is to make synthesis systems, so artificial movements, to be on this level. So we must work with real human data. So we can have three applications of audiovisual speech synthesis system. So I will now speak about audiovisual speech. We can have conversational agents, we can have interaction, we can have speech therapy. So in the first case, it means that we have a system that, for example, helps us to guide visitors through some city. And besides the fact that it's showing map and saying something to us, it communicates with us, and it's shown as a head of some nice person with a pleasant voice. And we can ask the person, and it automatically understands the questions and replies. Or we can have companions. We had a project on this, which was a project for elderly people, where the idea was to make a computer animated companion, which was presented with photographies, and these photos were uploaded to the system, and the system automatically was trying to communicate with the person, because, you know, sometimes people sit at home and their children and grandchildren don't have so much time for them. So this was idea, so how to entertain people with such system. Then another level of task is when we have just the communication, when we need to control some machine. In that case, we do not concentrate on so that in some machinery we don't need special beautiful face with a pleasant voice, but we need to get the information. And the last application is speech therapy, where we do not need special human likeness, but we need to, for example, show exactly what to do with the tongue to produce perfect speech. When, in case, for example, when children have problems to learn to speak, or in case when, for example, after some disease like aphasia, or aphasia is, I think, the correct name, where people lose the ability to speak. And the therapy is to speak with them, to talk to them, to let them repeat the word, because they have, their mind is okay, only the output is somehow broken. So how to start again the output is to do exercises. So they need therapists for all the time, a long time. Sometimes it's 2 months, sometimes it's 2 years, and then suddenly it starts like engine of car, but then you old car that you want to start. So, of course, there's not so many therapists, so it's the idea of the project is to provide computer technologies for that. For this, we would like to perform some behavioral studies. Actually, I have a lot of information in this presentation, so I will not probably go to big detail in each slide. Some slides I will have to go through faster. But if you are interested in this topic, you can just stop me right in the time, or you can ask me after the lecture, because it is compound of several lectures, and I do not want to be too extremely long. So behavioral studies means that we would like to study human behavior to design more natural and more intelligible artificial systems. So that the avatar is moving like a real person. So sometimes it must make a little bit mistakes. It must be so that we believe that it's almost human. With regards to methods of audiovisual speech synthesis, we can say that in history it started by two-dimensional speech synthesis. So what means two-dimensional? It means that we have an image of a face that is changed. In fact, we replay some videos, some short video movies. We concatenate these short movies. I don't know, do you know the word concatenation? Yes, are you familiar? So, if you imagine what is concatenative synthesis in acoustic, so this is the same in visual. We just concatenate some short videos, and you can imagine that at the edges of the short videos there are the same artifacts as in the case of acoustic speech. So we must solve this. So there are some other approaches involve some morphing methods. So morphing, do you know morphing programs? There in old times, maybe not. It's not popular now, but like 15, 20 years ago, in old computers, there were very popular these morphing programs that you put one face and another face, and it makes some changes so that it's 25% of one face, 75 of the other. And we can use this for moving between keyframes of the photorealistic 2D so-called talking heads. And later, with the development of computers and with the development of their computational power, full 3D systems started to be developed. So we started actually in that time where already these photorealistic two-dimensional talking heads were about to end, and most of the teams moved to full 3D systems. So we then have, in this case, full three-dimensional model of a head, or at least a face part, and in this model we animate the region of the lips and around, or later we animate the whole face to provide also extra linguistic information, like some stress or this. So you know that that stress in speech synthesis is done, or in speech is done by increasing the energy of voice, maybe changing the basic fundamental frequency. And how we work with stress in visual part. So visual stress means that we, for example, raise our eyebrows like this. So if you ask someone and you can feel the stress work not only by acoustic means but also by visual means. So we work on full 3D systems with a quite high level animation, high level 3D models. Audiovisual speech synthesis does have three components. It has acoustic component, it has a visual component. We can distinguish static visual component and dynamic visual component. By static visual component, I mean the static 3D model of a face, of a head, that can be fully artificial, or it can be based on real data of some real person. And the dynamic component means the data for control of the animation. So usually it is some key points, set of key points that moves and that animate, that move the vertices of the three-dimensional model. And of course the acoustic component, but I said that I will present the visual part, so I will not speak about acoustic speech synthesis here because it's the topic of my colleagues. So first what we need to do is 3D reconstruction of real face. We actually used some special system using stereo vision setup, which was done back in 2002, I think. We had several master theses on that. The problem was synchronization of the two cameras, so we solved this problem by using one camera and set of 4 mirrors. So you know that the camera, especially now, the camera is wide, very wide, so to put 2 faces that are quite vertical to one frame is no problem without loss of resolution. So this is how the system looks. I didn't say for static, say that for static data we used structured light projector that projected this line, this stripe on the face from straight direction, while the camera can look at the person's face from sides. So you can see that the stripe is modified by the different angle, and we can measure 3D information. So this is the resulting data, and in 3D. This is a resulting model. Last frame usually of the last frame of the scanning process was used for texture, so that we can map the texture, the photo of the person on the 3D model. Actually, it is long ago, and now there is a lot of technologies, modern technologies that are commercially available. So I will maybe explain in the last part of the lecture, but for the better processing of 3D images, we purchased a couple of 3D scanners. There is a lot of technologies in this domain, but I must say that most of them, absolutely almost all of these principles are based on structured light. We can have stereo vision that use 2 cameras, as I explained here. But anyway, we need to find correspondence of points. That's why we use the stripe, because to find correspondence of points on the face, it's very complicated. At the edge of lips, we can find the edge because there is big contrast. But on the non-contrast parts of the body, it's hard to find. So, or non-contrast parts of any 3D object that we want to scan. So all the commercial scanners use structured lights, either some stripes, either some patterns, rectangular, either some points like Kinect. If you know Kinect, which is the small appliance for computer or for games, for recording games, control of the games. So it measures 3D information by projecting from one direction, projecting of special pattern of points, and measuring distortion of that pattern from different angles. Actually, we use these commercial 3D scanners from a company called Artek, which is based in Moscow. So finally, we use Russian technology. And we should record dynamic 3D component. So for recording of control data, we use the same principle. So in this case, we use this principle of in the old system, we recorded the face or head model, and to record the control points for the animation, we use the same system without this projector that produced the stripe, but we attached reflective markers to the human face, and using these markers, using processing of the 3D coordinates of these markers, we recorded control points for the animation, for later control of the animation. So it was, you can see that it was in a dark room using special infrared lighting, which was provided by the camera. These standard cameras sometimes have so-called night vision, which means that they can record in the complete dark. Recording in the complete darkness means that they have their own reflector or their own lighting, which is in infrared spectrum, so that human cannot see it. So it seems that it really records in complete darkness, but it's not true because they have lighting only in the spectrum that we cannot see. So we use this system. So then we need to solve the problem of coarticulation, which is the problem at the borders of concatenated units. I told you about this in speech and in video, and in this case we have some control points either using keyframes, so using some static parameter vectors, or using some dynamic parts that are concatenated to another part. So at the edge, at the borders of this, we must make some coarticulation. Actually, there is a lot of various parametrizations. If we do not speak about keyframes only, there is a lot of muscle and physiological models. There is a lot of groups that are interested in this or that principle. It is based on their background. If their background is more physiologist or more biology oriented, they are more interested in muscle-based models. And we, as a technology or engineering group, we are more interested on just recording the 3D data and replay the 3D data, meaning the surface. We are not interested in somehow describing the processes below. So there is a lot of standards of using control points like MPEG-4 and FAP. FAP means face animation parameters, so it's general name for a set of parameters, and MPEG-4 is a standard for video, so this standard includes animation parameters for the head, for body, for movement of objects generally, but mainly human and maybe other objects. So our control points set is compatible with MPEG-4, and the control points are the black dots here, and you can understand that we move the vertices of the 3D mesh, but we have to move also the vertices nearby. So we have sort of method of influence zones that says how other vertices of the 3D mesh are moved together with the control point. So for example, what is the influence of the control point to vertices in neighborhood? And for example, in some distance already the influence is zero, it's no influence. Okay? Later we started to use full face mockup data, so we now can make modeling of the full 3D face animation. Of course, it is one side is that we have a technology to make full 3D animation of the full face, and another side is that we must know and understand how to control the data. control the animation based on the input data. For example, usually input data is text. So using text data, we have to perform some animation. So we must have rules or data how to move the cheeks, the rest of the face during the synthesized speech. Because for lips it is okay, because lips contain the linguistic information. But the rest of the face can contain other information, like a mood, if the person is in good or bad mood, if he or she is sad or it's something funny. Yes, so they make where is the stress, etc. So this must be taken into account. Then there is a lot of models how to interpret the data. So here is just mentioned that how many degrees of freedom do we have in visual speech synthesis in face animation. So actually we have artificial auxiliary bones, because animation, computer animation is driven by moving of bones. The body animation is based on a skeleton of artificial or virtual bones. So we have to do something like bones inside the face instead of muscles. One big problem that we are going to solve and or are solving now is the problem of retargeting. Retargeting means that we have animation control data based on some face, some specific object, let's say, or person that was used for recording, and it had some properties, some proportions or dimensions of face. Some people have face more like vertical, some like rounded. So to be able to use existing data or recorded data on some person, to use it on another person, we must use the method of retargeting. We must retarget this data to a new model. So actually, we use finally some software like Autodesk Motion Builder that is used for animation, and I will show you some examples maybe later from the book. And then we have it is also, this slide is composed of some research paper or several research papers where we try to establish some more general parameters than really these geometric parameters, because geometric parameters are exactly, they are connected to the shape and dimensions and proportions of the one specific model. So we proposed a set of parameters, for example, upper lip, vertical movement, jaw rotation, mouth width, etc. So this is to audiovisual speech synthesis. And I would like to continue by sign language synthesis and recognition. Maybe I can make some break and make some demonstration now. So maybe it will be so that I don't speak long time in one. So I can show you some example. Actually, it is example of real application. The application can be called virtual moderator. We were asked for this during the opening of new building of our Faculty of Arts. And actually at that time it was Institute of Art and Design, and it was renamed to Institute of Design and Art. Then it became Faculty of Design and Art. And when they opened the new building, they have now, it will be 5 years, they had the idea of the ceremony that wanted to have there something interactive. So we provided them. What I show you now here is the software that controls the animation. So, for example, we can put some text here, and it is then synthesized on the screen, so that you can see the result. I will switch to, split display, so that I will have now the controlling program, and you will see only the animation. So I just show you what will look now the program here in my computer, in my screen, and you will see full screen of the animation. So.
Milí studenti, tak už se utište, ať můžeme začít.
So what you can see is the visual speech synthesis provided on the model of a 3D model of artificial head. Actually, in this case, for the two demonstrations I will now show you, we used statues because it was the request from the Faculty of Art. And in this case, for the first ceremony, we used the statue of Jan Amos Komenský, who is, I don't know if the name is known in Russia quite well, but he was of Czech origin. He then lived a long time in Netherlands, and I think he is even an object of one old painter, and actually there is speculation that in some painting, a man this book, I don't know who is the author exactly, Rembrandt, or there was someone from these masters who was his friend, and they speculate that the man on this painting is Jan Amos Komenský. But all our schools, from basic schools to universities, have somewhere, either visible or in some storage, they have this statue. So also our pedagogical faculty provided us with the statue, and this was my first time with the scanner. So I scanned this head, and we made it moving and animated speech. So what you hear is acoustic speech synthesis in Czech language, and what you can see is the 3D model. So.
Dobrý den, jsem virtuální dvojník Jana Ámose Komenského a vytvořili mě odborníci na katedře kybernetiky Fakulty aplikovaných věd Západočeské univerzity v Plzni. Můžete mi říkat Ámosy.
So you probably not understand exactly the text, but
You understand.
you understand. So I think maybe not completely, but basically you know what it was presentation of our department. It was actually, I can tell you some remarks from that presentation, because it was done using two moderators. One was the real person going along down on the ceremony, and second moderator, it was a group or pair of two guys who were just connected. They work very well with each other. So the second one was sitting behind my laptop and was entering the text there. And it was funny because Jan Amos Komenský is the top, is very old guy, so he is above all authorities. So when they needed to shorten the speeches of VIP people like rector and mayor of the city, they used Komenský to somehow interrupt and shorten the presentations, which was quite funny that the rector, after 2 sentences, was interrupted by a very famous quote of Jan Amos Komenský, that short and from content very interesting messages will remain in the memory of users for a long time. So rector after that said just sentence, so that I would not prolong, and Komenský said, do not something.
Miloš, may I ask you, so yes. About this person, how do you know about his real speech, about his real specials? Maybe he has some problem with pronouncement or someone else. Who is speaking behind?
Yes.
Which person?
I think I can tell you, I don't know how to introduce, but it's some special moderator of Czech radio who provided us the voice. So of course the voice is not original to that person because it was not saved. So unfortunately, I must say we use the term virtual double or virtual clone when we have the face, lip movements, and the speech from the same person. I must say, unfortunately, we don't have recordings of it. And this guy had to speak 25 hours in special room, yes, for obtaining this speech synthesis. So we would probably not ask even that time. Maybe if you have some time machine, you can get back to some 17th century or so. So no, the voice is of course someone else, and also the lip movements are someone else. So only the statue, and even it may be that it's not real, that it is imagination of some artist. So you know. Then there was another ceremony 2 years later. I don't know if you know about the project European Capital of Culture, European Culture Capital. It is organized every year in 2 countries, and cities are competing with each other. So for 2015 it was in Belgium and Czech Republic. In Belgium it was the city of Mons, and in Czech Republic Plzeň won this European Capital of Culture. And it was a lot of events, and at this, again, our faculty was involved in this, and they decided to use again this virtual moderator, and they said, okay, maybe Komenský is not known because there were also some foreign guests of the ceremony. So they said someone else. So they were selecting the person for the moderator of the ceremony. So they said Mona Lisa would be fine. So they found, of course, you have the image of Mona Lisa. So, but how to make 3D animation? You must have 3D model of the head. So because they are faculty of art, they have also sculptures. So they made a sculpture of Mona Lisa from white gifts. We made the 3D scanning. So far we have this statue, and then they projected texture for this virtual statue. And then one more thing, if you notice that she's rotating quite a bit, so there are some parts of the painting that are in the original behind that. So these our painters also had to fill the rest of the painting behind Mona Lisa. So in fact, I can say that we are We are the only one in the whole world who knows what is behind Mona Lisa.
So now we can understand what multidisciplinary research really means. It was questioned many times that we should move also the other parts, but at this time we have really like statue, and only moving parts is around the lips. The next step is to move the whole face using the 3D facial data, and next step is maybe to take the hands apart, the arms and the hands, and maybe she can speak in sign language. So we can try her.
Здравствуйте, меня зовут Мона Лиза. Я родилась в городе Вязьме, очень люблю чешское пиво.
For Mona Lisa, for presentation, I use our Russian voice. Of course, it is not real voice of Mona Lisa, because we don't have, and actually it could be only speculation that she spoke Russian language. But I cannot use this for Jan Amos Komenský, because we do not have so many voices for other languages. We work on speech synthesis. So we have, in Russian language, we have just one voice, and this is female voice. So it would be strange if you hear Jan Amos Komenský with female voice. But so I can use it with Mona Lisa. So you can see the data for controlling the animation are the same as for Komenský. They are retargeted to different proportions of the head and body of Mona Lisa, and it is joined with acoustic speech synthesis in Russian language. So we just the data are same or similar, but we have to make mapping of vizims, because the vizims can be little bit different. So of course this is ongoing research for many years, that we work on audiovisual speech synthesis and sign language speech synthesis and recognition and audiovisual speech recognition in cooperation with another institute of Russian Academy of Sciences in St. Petersburg. So some parts are joint results of our cooperation that started many years ago. Okay, so maybe one more sentence, if so that don't prolong too much. But if you have some idea of what she should say, some question. Maybe if you are interested at the end, I can show you more. So I will switch back to this plot presentation and continue with sign language. When we want to synthesize sign language, we must somehow express it for computer processing. In speech synthesis, I mean voiced speech, it is quite easy because we have textual form and voice, which are corresponding to each other. While in sign language we do not have any textual form. So we use glosses as a one basic description, which is the name of signs. Actually, it does not contain all the information sometimes, because sometimes as the same, as I said, the same sign, the same gesture, manual gesture, is performed together with different articulation of lips or different face expression. But generally, when we want to translate voiced speech to sign language, we need to have some representation, and this representation can be based on so-called glosses, which are the names of signs, names of gestures. And then the next step is some symbolic representation of the sign language. So the same way we can symbolically represent the shape of the lips and somehow say, oh, some, for example, some vowels, some is different because it's very narrow, some is very wide. Yes, we can have some symbolic, some general parameters. So we have something similar here in sign language. It is actually a whole domain that is maybe part of linguistics of sign language that tries to describe sign language from the linguistic point of view. Like for speech synthesis, you need phonetic transcription. So you can imagine something that is similar to phonetic transcription in speech, but for sign language, where we don't have acoustic speech, we don't have, or we have articulation, but the main parameters are head, shape, orientation, position, and movement. First one, who started with this idea was William C. Stokey at Gallaudet University in 1955. Until he came to that university, American Sign Language was, or what we now call American Sign Language, was perceived or regarded as some images in the air that these people, because they cannot speak, so they are poor, they don't have communication needs, and they must somehow move hands in the air. And he started research that at the end proved that sign language is a fully fledged language, that it has all properties of full language, and it is completely different from this voiced language. So that's the problem of translation to sign language, or to sign languages, to any sign language, that we need to provide translation, like from Czech to German, from Russian to English, from Russian to Russian speech, Russian sign language. Because the grammar, the word order, the structure of the language is completely different. So he was the first to prove this, and he published some, at 55 or 65, he published some very important paper for that. And since then, sign languages are studied as full languages. One thing is to study them and to somehow describe them, and the second thing is how to graphically use it. So he used at that time sort of symbols that is provided here. So we can here can see some properties. It was sort of phonetic transcription, but you can see the last sentence. It allows rather discriminative than descriptive approach. So we have a lot of description of sign language, these symbolic notations, and some of them are very good to distinguish signs. We can use them for recognition, but they are not descriptive, so that we cannot make synthesis based on these symbolic descriptions. So Stokey is good for discriminative but not descriptive approach. Then one very important for sign language notation is Hamnosis, Hamburger Notation System, developed the first version in 1984 in Hamburg. and that develops. You can see these as are years of new versions of Hamnosis. Now it contains also information about non-manual component, but basically it is really phonetic transcription that uses symbols for providing information of how to produce the animation. So it consists of some symbols. I don't know if it can be seen, but there are symbols for hand shape. There are symbols for hand orientation, like if it is this way, palm towards body, or outside, or down, or up. Then up position, if it is upper body, below, sides. Then it has orientation movement, and then shape, orientation, position. Yes, and movement. And relation of the two hands. Sometimes we need them to relate. It can be, for example, I don't know now, that some gestures are the same, and they touch, these fingers must touch. So this is the relation that is in the symbolic description. We just symbolically describe approximate position. We don't have exact position in coordinates. So we must then say that exactly these two hands should touch in certain position, like this, or different sign will be when they touch like this or like this, for example. I don't know. So here is a sort of sign language editor that we created for this purpose, and you can see the list of hand shapes and orientations and positions and movements, etc. And so it is. These are parts of the sign gesture. So it is sort of like if we have a phonetic transcription for a word, we have also parts of the word, syllables, and the word is the structure consists of syllables and syllables from individual phonemes or triphones. So this is a very interesting notation for especially for the manual component. And then there is a lot of others, like AS alphabet, like alphabets for American Sign Language, AS alphabet. Then Dimsky's notation from Lydia Sergeyevna Dimsky's from Minsk. These are both based on Stokey notation. Then something completely different is sign writing from Valerie Sutton from 1974. She was interested in dancing, so she started this description of dancing, of movement and positions in dance. And then she said, okay, this maybe can be used similar strategy to description of signs. And then they said, okay, it can be used for any other movement, for sports, figure skating, movements, for pantomime, for gymnastics, generally all movements. So in the result of all this mind writing, sports writing, dance writing, sign writing, together is International Movement Writing Alphabet, IMWA. And this is how it looks. So it is nicely descriptive, but the problem is that it is not good for computer processing. So from Valerie Sutton, sign writing is very interesting parameterization or symbolic notation, but not very well used for computer processing. And then one of the next is movement hold by Little and Johnson, which is based on the strategy that the sign language consists of static parts, movement parts. So there are sort of keyframes and movements between the keyframes. So it is quite different from Stokey, but it is also it has good linguistic description, and it is maybe better for description of sign language than system of Stokey. So then we have animation of parameters, so we must describe the sign language, go from, I told you, this glosses, and then the symbolic notation. So then we have geometric some parametrization. So we go from glosses to geometric parametrization to control data for animation. So I told you how many bones we have in the face, so these so-called bones. So we have here, down you can see 68 degrees of freedom, because each finger, each arm, yes, so we can count there's 21 for palm, then 7 degrees of freedom for arm, then rotation position of this so it's 6 degrees of freedom, and we have two hands, so twice more, so 68 degrees of freedom. Then we must process the animation, so translate from this. I would say that there are two animation principles, two basic animation approaches, and one is rule-based and second one is data-driven. It's in all domains of synthesis of everything that we can have rules. And for example, I can show you example of the sign for word train. Yes, in Czech sign language, the sign or the gesture for train is something like that. You can imagine the old locomotive or something. So we describe the movement, we describe symbolically position, orientation, shape of the hand, and rotational movement. So if it is rule-based, we are at the technology level, so how would you describe the rotation movement? By some equation of a circle. X squared plus y squared is equal to r squared, yes? Show me a person that uses in real signing a gesture that is exactly on this equation of a circle. So it is perfect animation from this technical point of view, because we have mathematical description of the circle, but it is not natural. So probably it would be intelligible, but not very natural, because this movement will be not done by a real person. And the same is if we have keyframes and then movements, linear movements. So we can say, okay, linear movements are not problem, but if we have keyframe and then linear interpolation to another position in keyframe and another, so it is also not very natural. So real human gestures have much bigger dynamics and not really linear interpolation movements. So this is argumentation for using data-driven approach. Data-driven approach means that we record data, record movements by real people, and then we replay these movements, but we must combine them. We can record all the signs. The easier way is to record the whole signs, but then we have problems when we want to add some signs, some new words to our vocabulary. So we must ask the same person so that it is with the same proportions of the body. We must ask him to probably to use the same way of signing. If he can at all find the person, or maybe he moves somewhere and we cannot ask him. So the idea of our system that we are building now is to record all possible movements, all possible parts of signs, like all possible shapes, movements, positions, orientations, etc. So that we can combine, like in the case of speech synthesis, we combine short, like in our case, what you've heard, it's triphone-based speech synthesis. So we concatenate triphones, which is phonemes, in a specific context, left and right context. So we don't have all words recorded in our database. We produce new word by concatenating phonemes from different words. So it is the same here. We don't have this different sign, but we have this shape from different sign. position from different, and we combine this and retarget to new proportions of specific avatar. So then we have to solve the problem of co-articulation, because when we record the signs, usually we start in some basic position, then we make a sign and go back. But in real signing, we don't go back. It's like the difference between continuous speech and isolated words. So it was a big topic to move from isolated words to continuous speech. Let's say, no, when I entered university as a PhD student, it was a big topic, because until then it was isolated words was something big research result, and now we have speech recognition of continuous speech. So it is the same here, continuous signing. So we must solve the problem of co-articulation. Then, of course, we have also the 3D static data, which is now some 3D avatar, 3D animated model, which in fact now can be any model. There is a lot of models. There is even character generator. Autodesk has a software that you just select if it is male or female, the age, the proportions, color of hair, color of eyes, everything, proportions that you want in your avatar, and then it generates the virtual body, and it is provided with the bones for animation. So we just need to provide data for the animation. In this case, it is our 3D model. It was a real, what I call virtual double, because audiovisual speech synthesis using this head was done by the same person for the head model, same person for animation control, same person for acoustic speech. Yes, and then we must provide the sign language synthesis. So I can show you example of synthesis, but I will first say a few words about sign language recognition. So in case of recognition, it is different, because we don't have this data for animation. We don't need this. We need to vice versa, to recognize, to add parameters. In case my presentation does not contain audiovisual speech recognition. Yes, because it was not part of these lectures, but you can imagine that we somehow record face, record the lip movements, lip shapes, and beside acoustic parameters of the speech, we attach some parameters for visual part. And there are 3 levels of combination of this data. Either we just combine parameter vectors and then we put it to some recognizer, or we have 2 recognizers and then we combine results of the 2 recognizers, or we have some combined recognizers, some multi-stream hidden Markov models, for example. And then here in sign language, we have something similar, but we have to somehow analyze and find the hands so that we can describe these parameters: shape, orientation, position of hands. So if you look at me and you imagine that you are the automatic system for recognition of sign language, it depends from which direction you look at me, but if you imagine me in front of this, it will be hard to distinguish the hand from the background. So it is, of course, easier in a contrast background. It depends on clothes, it depends on, for example, other properties of face, length of hair, etc. So now in the recognition, the task is here in the recognition, the task is more complicated. So we must detect and track hands and face. So we have 3 objects to detect and track. then describe basic parameters, and then recognize. So here in this case you can see one of my PhD students, actually former PhD student, he's now a researcher in our lab, and he shows some sign, and here you can see the process. But you can imagine that when the two hands are occluding one each other, when they touch each other, or when they are occluding the face, so then it is bigger problem to distinguish the left, right hand and the face, distinguish these three objects, and then to even to describe them. Where to use this technology, of course, in sort of kiosks. So when I spoke about embodied conversational agents, it is the second case here. We have sort of kiosk that is that can be used, for example, when the person comes to train station, and we ask the seller by voice to buy a ticket to St. Petersburg by Sapsan at 7:30, and then an automatic machine will recognize the voice, maybe using the lips, and then it replies by speech synthesis. In communication with deaf people, we need to have recognition and synthesis of sign language. So otherwise, the general principle is the same. Then another, for us, very interesting example of application is TV, because Czech TV, I mean the public one, needs to provide 70% of broadcasted material by translation for deaf people. It's by law. It's written in law. The public television must do this. So one thing is to convert speech to text, to hidden subtitles, and another is to translate to sign language, to real communication means of deaf people. So the project of speech to text, it is not my domain, but it is a real project that was already partially finished. So for most Czech programs, Czech TV sends the speech, the voice to our laboratory. There it is automatically converted to text. It is sent back to TV. So if you, at specific programs, if you switch to these hidden subtitles, it is provided by our automatic technology. And in the programs where there is a heavy speech, a lot of people shouting cross speech, yes, it is not possible to recognize, so we use the technology of shadow speaker. So there's someone who translates from Czech to Czech, but to clean speech. So our idea is to provide in future TV with automatic translation to sign language. So probably it would not be for all televisions, but you will buy a sort of set-top box, like when we switch to digital TV. We have to have some box, and in this box it will be connected to signal, and it will be connected to internet. So we will just select avatar, we download our familiar avatar, some 3D model of some actress or whoever, and then it will show, everyone will have its own avatar. And then next application is, of course, teaching of sign language. This is some drawing of our prototype of kiosk. So there is big screen rotated 90 degrees, because in vertical screen it's better to show the avatar. Two cameras for 1 and 2 for stereo vision. In this case, we put cameras in this vertical position so that the kiosk can be quite small. And the third camera is like zoomed to a face, so that it records lip movement. And then there is touchscreen display, because sometimes we can use the maximum of sign language technology, but sometimes it's easier simply to tap the screen, because if you have long names of some cities, then you can how to say, by finger alphabet, you can provide a name, but sometimes after 3 or 5 letters, it's already several possible names of cities, so it's faster simply to tap the screen. So now to technology. Before technologies, I will show you example of our sign language avatar. So you can imagine that this is the board at the train station showing the list of trains, and for example the message that goes by voice is provided to travelers, and in this case we make animation or translation to sign language. When I turn on this, oh, it's very dark, but if you can see the names of the signs, so this is what we call glosses. These words are what we call glosses, names of the signs. It's fully 3D model. It's rule-based animation. So you can see that the movements are a little bit like not very natural, but if it is combined with articulation, it is intelligible. Okay, I think it's enough. So in the last part of the presentation, I would like to present our technologies. There is a lot of them. It is a big institute, but I will say only about my laboratory. So my topics include, besides multimodal or visual human-computer interaction, generally computer vision. So I have 3 groups of PhD students, mainly in these 3 domains: industrial computer vision, medical computer vision, and this HCI, human-computer interaction. So especially the equipment went for HCI when we need optical body motion capture system and facial motion capture system, and then hand gloves, because optical system is not useful for detailed tracking of fingers. So I will show you this technology. The main one is motion capture technology. I say it's my flagship. It is a technology that is used for movies. It is company Vicon provides movie studios with this technology, and we want to use it for recording and VR recording data for control animation of sign language. So you can see that it's a set of cameras. We have 8 cameras, 2 megapixels each. These cameras have own processors, so that they process already the information and sense only the coordinates of the recognized markers. So, for example, here you can see the 2 actors, and you can see the small markers. It's 14 millimeters round reflective markers from reflective material that are attached to the body. They are attached to the special suit that is made from Velcro material. So the markers are done at some cross-shaped platforms that are from the Velcro hooks, while the costume is from Velcro these loops, and how it is called, loops and hooks, I don't know. And so it very firmly is connected to the body. If you use just the two-sided adhesive foil, it is more likely that because people during the presentation start a little bit sweat, so they then disappears. So the system can record in this even more than one person. You can see in this case it is a hall that is called theatre. It will be future theatre of Faculty of Art. It is the biggest hall in our university. It's 15 by 15 by 7 meters, and it can be very well captured. And software of Vicon Blade records the movements from the structure of markers. It converts to structure of bones, to the skeleton, sends the skeleton in real time to Motion Builder, which is the animation program, and then animation program can in real time reproduce these movements. So you can see that on the board present by projector from the computer, already reanimation in the real time of the movements that are provided by the actor. So they made some jokes with moving chair. So for example, swimming, how you make swimming without a pool. So a person was in a chair and the second person moved him and he just made the movement. So then you can see that in real time we can, of course this is from some presentation, but the research goal is to record data for animation control of sign language and solve perfect linear retargeting and solve a combination of parts of the signs, not only replay of the individual signs. The individual actors can be distinguished by special marker sets, so some code, and every person has different this code, so the system can distinguish these two from each other and not mix. Sometimes when they, for example, perform some dancing, so you can imagine that these people, when dancing, they are very close to each other, and the system can split, can mix the two some points of the two persons. Then the part of the system is also Vicon Cara, which is this sort of helmet with 4 cameras, 1 megapixel black and white only, and this can record markers attached to speaker space. We have much more markers than in case I show you for audiovisual speech synthesis in the old times. So we can record movement of the whole face. Actually, this was developed for the movie Avatar because it was first movie where there was so many dialogues, where there was needed so big amount of face animation that it was cheaper to develop such system than make handmade animation. Until then, it was cheaper. And sometimes people at animation studios, they do not want to use this because they lose their jobs, because human animators that by hand do all the animations for movies, they are replaced by these technologies, which is better because it records real movements. It is not artificial, artistic. So we can distinguish between artistic approach when the artist provides data for the animation, how he thinks that it will be, and data-driven when it is real movements of real person. So here it is real movements of the face. Then hand tracking data glass, because as I told you, especially in sign language, there is a lot of signs where you have fingers that are close to body. So you can imagine that these markers goes to body, and where is the camera that can see? It is problematic. We don't need more than 20 cameras to do this. Yeah. So we use not visual based, but band based. It's mechanical sensors that are measuring the bending of figures. Then we have a set of eye trackers. So this is not already for exactly for this real animation, but it is for the behavioral study. For example, imagine I told you in the beginning about the multimodal communication. So we said it is speech, you hear me. It is audiovisual speech, you look into my lips. Maybe if there is a noisy situation, there is some trams or cars running. So you will more rely on my lips, and when I turn around you will not understand so much. Then there is eye contact, which in eye contact in hearing people is obvious, because we do not need to look at lips all the time. Maybe from some time when the tongue just goes along, but otherwise we look into each eyes. And now imagine a communication of deaf people. Usually people designing their animation, they think about perfect animation, how we make it absolutely precise. But behavioral study can provide us with information. What amount of time do these people look exactly at precise animation, focused to exactly both hands? What part of time do they look at lips? What part of time do they look into each other's eyes and perceive the hand animation only by peripheral vision? Which means that we don't have color, we don't have exact position, we have movement. We have, yes, by peripheral vision we are sensitive to movement of something contrast. So from the point of view of us designing the technology, it's not important maybe sometimes to make absolutely precise animation, but the overall image, the overall perception must be done. So my idea of performing research is to measure two deaf people communicating with each other and measure what part of time, let's say in percentage they look into each other's eyes, into hands, into lips, some other parts, somewhere the window. Yes, so this eye tracker has a camera that looks to it's half mirror glass that it sees reflection of the eye in special spectrum, while we can see through the user can see through the glass. And the other camera that is hidden maybe a little bit behind here, it sees the view of the person. So it projects detected eye gaze, the direction of gaze, to the other camera, to the image from the other camera. Then commercial 3D scanners, I already mentioned. Then we have thermovision camera. Then we have a lot of industrial cameras, manipulators, other technology. We have it is not connection to video, so I didn't put it into the presentation. But we have electromagnetic articulograph. Do you know what is electromagnetic articulograph, or should I explain a little bit? It is a system for motion capture of the articulation. So articulation is performed by what? Basically by tongue, by inner part of mouth. So how we can measure? Actually, vision-based methods cannot be used because we cannot see there. Only some ultrasound, or of course we do not want to use X-ray because it is harming person. But ultrasound maybe would be a solution, yes, in this. And electromagnetic articulograph uses special small coils that are attached to the tongue. They are provided with some special signal that is given to them by wire. So you have several coils attached to your tongue and wires going from your mouth to the system. And then you have quite a sort of, again, helmet, but it measures 3 positions of invisible coils inside because it's electromagnetic waves. So it is much more precise measurement of articulation. So my colleagues from not science speech synthesis, acoustic speech synthesis part of the department, they have it and they use it. So for other domains we have building full of equipment. So I just explained one small part, not so small. When I bought this equipment during the year, so I think it was not so bad shopping. But now it's also mainly on my PhD students to work with these systems because one must also be interested by some administrative works, etc. So thank you for your attention.